Hi-oh, here we are again. We're going to continue by talking about free fall, only this time with air resistance. Nice little cartoon to get us started. As the first duck kept Margaret's attention, the second one made its move. How absurd. So funny. All right, little backyard physics by Paul G. Hewitt. The lady is asking the two gentlemen below which will hit the ground first, the bag of clothespins or a single pin. Well, the guy in red, he's more of an Aristotle type of guy. He says exactly what Aristotle would say. He says the bag of clothespins is heavier, which means gravity pulls on it with more force. So, right, F equals ma, more force, more acceleration, it'll hit the ground first. Sounds pretty good, and most of that sounds really good. In fact, it is heavier, it does get pulled harder, therefore it should accelerate. However, the guy in purple says, no, the clothespin has more mass, and we know Newton's first law says mass is inertia, so it'll be less responsive to gravity and lag. So we have two contradictory ideas. And it turns out they both hit the same time. Now why? For exactly the reason both of them said. One should accelerate more, but at the same time it has more inertia. Mathematically, we can look at this and know F equals ma or A equals F over m. Well, remember, the amount of mass you have is directly determined or will directly influence your weight. So if you have twice the mass, you also have twice the weight. Why? Because gravity is still accelerating things at the same rate. To keep A the same, or G, as you increase the top, you should increase the bottom. It has to stay proportional. So things fall at the same rate. Doesn't matter. Hammer and feather on the moon. They fall at the same rate. But when we get air resistance into the mix, that's another story. Now we have a net force to consider. So when we put that air resistance in, we eventually reach something called terminal velocity. And that's exactly how it suggests. Terminal meaning end, velocity, so it stops speeding up. The air resistance balances the weight. The guy just doesn't hover there like our little skydiver guy. He is still falling. He's just not going faster. Human body is about 110 miles per hour in the position that guy is showing. That's about how fast you would go. So the net force at terminal velocity, think about this. Remember, if you're not speeding up, you have zero acceleration, therefore the force is zero. So let's look at our skydiver. Guy that jumps out of a helicopter, the force on him, the force of gravity on him, that's his weight, right? The more mass you have, the more weight you have. You notice, force of gravity, that's the net force. It's just him, nothing else. We now have some air resistance involved. Look what's going on. Net force, 1,000 down, 200 up, for a net force of 800 down. All right, it's down. The weight is down, air resistance is up, so the net force is down. Does his weight change as he falls? No, he still weighs the same. Did his mass change as he fell? No, he still has the same mass. But the net force changes because the amount of air resistance he encounters changes. Once the net force is zero, as we established earlier, you are at terminal velocity. He's still falling. Net force zero. 1,000 up, 1,000 down, net force zero. He's still falling. He's just not going any faster. Suddenly he pulls a chute, starts catching a little more air. We have a greater force up than down than his weight, and therefore the net force is positive. Catches more. Eventually it catches up with him, only catches so much, and he starts slowing down, and this is the second time he reaches terminal velocity. The first time he reaches about 120 miles per hour. The second time, about 30. The parachute causes him to slow his descent. So you can think of the parachutist similar to a car. If you get inside your car and you push on that accelerator, it's going to speed up, speed up, speed up, but will it continue speeding up forever? Of course not. What happens is the car encounters more and more air resistance, and eventually the air resistance equals the force that the engine can apply to those tires to get them to grip the road. Once they equal out, you won't speed up. You will not accelerate. So let's develop this just a little further. We have this skydiver on the plane to the right. You can see newtons all the way down. We can see an arrow in newtons going up. Just like in our examples, the arrow down must be his weight. How much does he weigh? Of course, it's 600. Is that changing? No. Does his mass change? No, of course not. He can go to the moon, he'll still have the same mass. Does it? So does any of that change? Absolutely not. How would we find his mass if we know the weight? Well, F equals mg. G is 10. This is his weight. We would solve for m. But in this case, it's given to us. His mass is in kilograms, weight is in newtons. So how would you figure out the acceleration at each position? Newton's second law. Very simple. What's the net force? Let's pick, I don't know, how about D? We have 900 up and 600 down. That's a net force of 300 up. And of course his mass is 60. And this is of course in newtons and this is in kilograms. And therefore the acceleration, 30 divided by 6, and that's 5. And you can try that to see if you get those numbers. We're going to need those numbers to answer some questions about our skydiver. So, where is he experiencing upward acceleration? You have to realize that sign tells you everything. When it's negative, that means down. When it's positive, it means up. So, where's the upward acceleration? At point B, because we have a positive 5 meters per second per second. How about downward? Test it, A and B, because they have a negative acceleration. How many times does he experience terminal velocity? Terminal velocity, the net force has to be 0 when that happens, and therefore acceleration is 0. So twice, C and E.